Welcome to the video on recurrent neural networks. So what is a recurrent neural network, which is often known as an RNN? Okay, so the first thing is that the normal neural networks that we have discussed earlier, right? So they do not have any persistence. Now what do I mean by persistence? It means that they cannot store any older information that can be used later on. Okay, so RNNs have persistent and they have the loops that can allow the information to persist. Okay, so in the cases where you would be needing the older information so as to process the current inputs, that is where recurrent neural networks are used. Okay, so these RNNs, they can use their internal state to process the sequence of inputs. Okay, so you can just think that whatever has happened in the past gets stored in the memory of an RNN. Okay, so internal state or memory, you can just use these words like synonymously. So the past events, they get stored in the internal state or memory of the RNN, and then this memory can be used for processing the further inputs. Okay, so hence this property of the RNNs makes them applicable for the tasks such as unsegmented connected handwriting recognition or speech recognition. Now let us see what are long-term dependencies. So the late output depends on a very early input which has to be remembered. Okay, so in the case of long-term dependencies, this is what really happens, right? So suppose there is a very early input, and we'll discuss about this in some example that's just coming. Okay, so if there's just some event that has happened long ago and you want to have its information to give some output later on. Okay, so this is a case of long-term dependency. RNNs are supposed to connect previous information to the present task. So this is what we have discussed, right? If the gap between the relevant information and the place where it is needed is small, RNNs are able to work well by learning the use of the past information. Now, where the gap is huge, RNNs are not able to learn to connect the information. Okay, so sometimes what happens is that suppose we say some sentence and the context is very clear. For example, it is raining outside and the road is wet. Okay, so this wet, the last term of the sentence, it is pretty obvious, right? So because you know that it's raining outside and then definitely the road has to be wet. So it's a very little gap between the previous context of the sentence and the last word. Okay, so we're talking about the rainy weather, right? So it is like pretty obvious. So hence here we say that the gap is pretty small. Okay, but suppose just consider the sentence, I was born and brought up in India and I speak fluent Hindi. Okay, so here the gap is slightly bigger. Why? Because I was born and brought up in India, this does not directly imply that I am fluent in Hindi. Okay, because there are many Indians who are not fluent in Hindi, and then if a person is born and brought up in India, he or she may be fluent in more than one languages also, right? So it is not very obvious that the word Hindi will come in this sentence. Okay, but in the case of it is raining outside and the road is wet, this word wet is pretty much obvious. Okay, so hence we say that in this sentence, it is raining outside and the road is wet, the gap is pretty small. And in the sentence, I was born and brought up in India and I speak fluent Hindi, the gap is slightly bigger. Okay, so the RNNs may be able to work well in the first case, but they might have a difficulty in predicting the word Hindi in the second sentence. Okay, now let's talk about LSDM networks. So this LSDM networks basically stand for long short-term memory networks. Okay, and these are a special kind of recurrent neural networks that are able to learn the long-term dependencies well. Okay, so basically what happens is that these RNNs, they have repeating modules of neural networks, right? So that happens in the LSTM networks also. So we'll be discussing LSTM networks in detail in this video. So basically, in the chain-like structure of the LSTMs, each repeating module has 4 neural network layers. Okay, and the interaction between these units occur in a very special manner, which actually dictates how the LSTM works. Okay, so yeah, let's see the step-by-step working of each of these modules in the LSTM network. Okay, so this is a basic LSTM cell, right? And you can see this horizontal line on the top, right? This one. Okay, so this is known as the cell state. Okay, and it just runs straight down the entire chain with only some minor linear interactions. So it is very easy in the case of an LSTM cell for the information to just flow along without being changed or modified, right? So the LSTM has the ability to remove or add information to the cell state, and this is done by these structures which are known as gates. So for example, you can see this thing, right? So this is a gate. So basically information just flows along the cell state, and you can use these gates to modify like how much information will just flow along the cell state, and is it something to be changed or what. Okay, so these are the gates that are used to modify the cell state information. Okay, so these gates are a way to optionally let the information through, right? And these are composed of these sigmoid layers. Okay, so basically what happens is the sigmoid layer, it just outputs numbers from 0 to 1. Okay, so if it outputs number of 0, then it means that nothing is to be just passed through this cell state, because this is a multiplication operation over here. And if the sigmoid layer just outputs a value of 1, it means that everything is to be passed through the cell state, because this is a multiplication operation over here, right? So basically let's now just see step-by-step walkthrough of each of these layers. I mean, how do they affect the cell state? Okay, right. So the first step in a LSTM network is to decide that what information we are just going to throw away. And yeah, because when you want to just modify some information, so we will also be needing to just discard some information, right? So this is done in the very first layer, the sigmoid layer. So this layer is also known as the forget gate layer. Okay, and the input to this layer are this ht1 and this xt, right? And after the sigmoid operation is being done, so it just emits a value between 0 and 1. Okay, and then this number is just multiplied with this cell state ct1, right? And if it just outputs 1, so all the ct1 just pass through, and if it's 0, then it just get discarded completely. Okay, so basically the equation for this ft is sigmoid of wf into ht minus 1 comma xt. Okay, so this is just a multiplication plus bf, right? So essentially this is again, I mean, just a normal sigmoid layer as it works in a neural network. Okay, so it's just sigmoid operation on this computation. Okay, so through this we get to know that what information is to be discarded and what is to be kept, right? So yeah, so now let's just talk about this part. We have to decide that what new information is to be passed on and to be stored in the cell state, right? So now this thing has two parts. So firstly, what happens is that there is the sigmoid layer, okay? And this sigmoid layer is also known as the input gate layer, okay? And the work of the sigmoid layer is to decide what values are to be updated, right? So this sigmoid layer essentially just releases a number between 0 and 1, and accordingly we decide that what information is to be updated, okay? And then we have this tanh layer over here. So essentially it creates a vector of new candidate values ct bar, okay? So you can just see it, and these values, these new values, they can be added to this cell state, this ct1 that's just going on, okay? And now how much of this ct bar we'll be able to add to the ct1, ct minus 1, so that is regulated by this sigmoid layer, okay? So suppose we have like several elements of this vector ct bar. Okay, but when it's multiplied by with this sigmoid with the vector that we get after the sigmoid layer operates, so essentially this it bar, so by multiplication some part of the ct bar may be discarded. Okay, and the effective one is added in the ct minus one. Okay, so this is how the updation takes place, right? So essentially we can write the relevant equations as this it equals to sigmoid of wi multiplied by ht minus 1 comma xt, okay, plus bi, okay, and the ct tilde or ct bar, whatever you want to say, it's equals to tan h of wc dot ht minus 1 comma xt plus bc. Okay, so these are the relevant equations. So you can just see that for this one it's a sigmoid of wi multiplied by ht minus 1 xt, which are the parameters to this layer, and bi is added, right? And for the ct bar also you can see that this equation holds true. Okay, okay, so now we actually add the results that we get after multiplying these it and ct bar. Okay, and we add it to the ct minus 1. So essentially what happened till now is that we had this sigmoid layer, which is also known as the forget layer. So it actually discards some of this information from the ct minus 1, and then later on this effective thing that we get after it has been multiplied with ct bar, so that has been added to the ct minus 1. So essentially what has happened till now is that we have discarded some of the old information and we have updated the old information with the new information. So this has what has been happened till now. Okay, so from here onwards we get this ct, so which is essentially the updated cell state, right? So the ct is equals to ft multiplied by ct minus 1 plus it multiplied by ct tilde. Okay, so you can see that this equation actually holds true. So ct equals to ft multiplied by ct minus 1 plus it multiplied by ct tilde. Okay, so this holds true. Okay, so the last step is to decide that what is going out as the output of this LSTM cell, right? So this output will be based on the cell state, right? So you can see that the CT is used, but it will be a very filtered version, right? So essentially what is done first is we have the sigmoid layer and it works upon this HT minus 1 and XT, okay? And it releases this OT as an output. So essentially this takes care of what is to be retained and what is to be discarded, okay, because this is a multiplication operation over here. And then we actually have this CT, which is the present cell state, and it runs through this tanh operation, right? And yeah, so essentially the task of this tanh is to just scale these outputs, like because the output of this tanh it will be between -1 and 1. So as to push the value between -1 and 1, so we use this tanh operation, okay? And the output of this tanh operation and this OT, it is multiplied, and that is just sent across as the output for this LSTM cell, right? So this is what happens overall in an LSTM cell. So the relevant equations for the last state can be that this OT equals to sigmoid of WO multiplied by this HT minus 1 comma XT plus B naught. Okay, so this is for the OT, and for HT we have OT multiplied by tan h of ct, right? So this is basically how a single LSTM cell works. So essentially this cell state, it will help in maintaining memory for the previous events that have taken place, okay? And there can be slight modifications, but this memory can just flow through across all the LSTM cells in the recurrent neural networks. And for each of this LSTM cell, there will be some output, right? So that output has been calculated, and yeah, so these are the equations, and in this video we basically saw that how does a single LSTM cell works.